When it comes to atmospheres, the planets in our solar system seem to have a monopoly. Like, of the 150 or so moons out there, only one has a meaningful atmosphere: Saturn's moon, Titan. But it holds its own. More than 1.5 times the density of Earth's atmosphere, Titan's is so thick with fog that visible light telescopes can't see through to the surface. Except for what we know for sure about Titan, it seems like that atmosphere should have disappeared millions of years ago. So why hasn't it? Scientists are still learning more, but new insight might be coming from a surprising source: slowly baking comets. In general, atmospheres aren't easy to come by. Big planets like Jupiter and Saturn had enough gravity to collect gas from the cloud of material around them back when they first formed. But smaller planets had to grow their own. Like Earth's and Venus's primitive atmospheres were belched out by gassy volcanoes and supplemented by molecules from asteroids. But on Titan, the situation is even trickier. See, Titan's atmosphere is made almost entirely of nitrogen, with about 5% methane added into the mix. And the haziness comes from chemical reactions between sunlight and the top of the atmosphere, which produce organic molecules that create that golden fog. But here's the thing. Because light is constantly breaking down the methane to make this fog, scientists calculate that it'd be completely gone within about 20 million years. So something must be replenishing it, or it probably wouldn't be around for us to see. Also, even though Titan is a similar size to Jupiter's moons Ganymede and Callisto, it's unique in having an atmosphere. So any explanation needs to account for not only why Titan has an atmosphere, but also why the solar system's other big moons don't. One explanation scientists have proposed is that Titan's atmosphere is related to how it formed. Specifically, one way that Titan could have gotten its nitrogen is via water ice delivered to the moon during its formation. After all, lots of different compounds can get trapped in bubbles inside ice and hitch a ride around the solar system. So some scientists in the 1990s suggested that Titan may have been bombarded by comets full of ice loaded with ammonia, a compound that contains nitrogen. Over time, the ammonia would be slowly released from the ice and converted into nitrogen to fill the atmosphere. As a nice bonus, this can also help explain why Titan has an atmosphere while Ganymede and Callisto don't. For one, Jupiter is a lot bigger than Saturn, so it was hotter, essentially causing the water on those moons to boil away. But also, its greater gravity would have accelerated comets into its moons faster, blasting the ice away from their surface. That said, this hypothesis can't really explain the origin of Titan's methane. To be fair, comets can contain methane too, but the comets we've studied up close, including Halley's comet, seem to contain a different type of hydrogen than what's found in Titan's methane. At first, this was a big blow for the comet hypothesis. The chemical fingerprints of cometary ice and Titan's atmosphere didn't match, so this probably wasn't the source of Titan's air. But then came the European Space Agency's Rosetta mission. When Rosetta arrived at the comet 67P Churyumov-Gerasimenko in 2014, it brought comets back into the picture. See, data from Rosetta revealed that the comet was half ice, around a quarter rock, and about a quarter organic material. The fundamental building blocks of organic compounds are carbon and hydrogen, the same elements in methane, but nitrogen is also a common element. So in a 2019 study, researchers presented a new hypothesis, in which this organic material could be the thing supplying Titan's atmosphere. They suggest that if Titan formed from comets like 67P, then it probably has a significant amount of organic material trapped deep inside it. If Titan's core still has heat left over from its formation, then some of that material would kind of be baked, heated up so that it releases compounds like nitrogen and methane. Their models suggest that at least half of the nitrogen and all of the methane in Titan's atmosphere could come from cooked organics in the moon's toasty interior. The main catch? If it's being produced in the core, all that gas has to make its way out somehow. On Earth, that often happens thanks to volcanoes, and some icy bodies may have something similar, called cryovolcanism. Cryovolcanism works kind of like terrestrial volcanism, except instead of molten rock, the lava is made up of liquid water. In both versions, though, eruptions produce billowing plumes of gas, and these cryovolcanic gases could be the thing to feed Titan's atmosphere. Only scientists haven't found definitive evidence of active cryovolcanism on Titan yet. It's possible that the gases are being slowly released from underground reservoirs hidden beneath the moon's unique lakes. But with so little data about Titan's subsurface, it's hard to say for sure. Ironically, the moon's thick, hazy atmosphere makes it tricky to answer questions about how it formed. NASA scientists hope to finally address these questions with measurements of the surface and atmosphere made by the Dragonfly mission, which is due to launch in 2027. Until then, though, trying to understand the mystery of Titan's atmosphere could help us understand more about how all atmospheres are born and how they evolve over time. And who knows? The comet hypothesis was almost ruled out because we just didn't know enough about different kinds of comets. So as we learn more about Titan, maybe we'll find a new way that those gases could escape too. Thanks for watching this episode of SciShow Space. We're able to explore topics like this because of the support of our patrons on Patreon. So to our patrons, thank you for helping us make the internet a more curious place. And if you're not a patron but want to learn more about becoming one, you can go to patreon.com/scishow.